Hi everyone, I hope you're doing well. I am Prabhu Chinnasamy and I work for Walmart Global Tech and my work location is Sunnyvale, California and United States of America. I am excited to share my work on AI-powered predictive analytics for cloud performance optimization. This is based on a detailed review and real-world experimentation around an architecture we call SPAT framework, designed to reduce downtime, optimize scaling, and detect anomalies in real time across modern cloud environments. Here is a quick overview of what we will cover in this presentation. We'll start with the background and problem we are trying to solve, then explore how AI-driven monitoring can help and I'll walk you through the proposed SPAT framework, the methodology, our experimentation results, and some real-world case studies. Finally, we'll touch on future directions and key takeaways. At a high level, our solution uses machine learning models like PyCaret, LightGBM, XGBoost, and Isolation Forest to enhance cloud monitoring. It delivers measurable outcomes, a 40% reduction in MTTR, 25% fewer false positives, and the ability to detect failures 30 minutes in advance. The system has been validated across retail, healthcare, and finance sectors, all highly dynamic environments. The problem context here is modern cloud systems are complex and unpredictable. Static monitoring tools often fail to adapt to sudden traffic surges or emerging failure patterns. Whether it is an e-commerce flash sale, a financial quarter end load spike, or pandemic era surge in healthcare platform, traditional rules just can't keep up. Industry trends shows that 80% of enterprises are moving to hybrid or multi-cloud setups. AI ops is expected to be adopted by 40% of companies by 2025. Major outages like AWS in 2021 or Azure authentication in 2022 remind us how critical it is to shift from reactive to proactive monitoring. Related work in cloud monitoring. So the traditional tools like Nagios, CloudWatch are rule-based and reactive, often missing early anomalies. AI apps platforms improve this but still suffer from model drift and lack explainability. Our hybrid AI approach uses ensemble models to boost accuracy while reducing false positives and cost. Here is the overview of SPAT framework. SPAT stands for System Performance Prediction and Anomaly Detection. It combines supervised learning for accuracy and unsupervised methods for flexibility in one integrated pipeline. It also plugs directly into CI/CD pipelines and is optimized for both cloud and edge environments, enabling real-time detection and remediation. So, this diagram represents the SPAD architecture, our system performance prediction and anomaly detection framework, which integrates multiple stages of AI-driven monitoring into a cohesive closed-loop system. In data collection, it all starts with the continuous metrics injection from sources like Prometheus or cloud monitoring APIs. We gather both historical data for training and real-time metrics for live predictions. In model training, we use historical data to train machine learning models, particularly with tools like PyCaret and LightGBM, optimized for performance and interpretability. In model validation, once trained, models are validated using standard cross validation and, in some cases, synthetic failures to ensure robustness under real world conditions. In prediction phase, in prediction system phase, incoming live metrics are sent to the prediction system where KPIs like CPU usage, memory, or response time are forecasted. In anomaly detection layer, these forecasts are passed into an anomaly detection engine where models like isolation forest evaluate deviations from expected behavior. Sorry. In monitoring and alerts, if anomalies are detected, the system triggers alerts and monitoring dashboards to inform DevOps or SRE or engineering teams in real time to take action. In the feedback loop, detected anomalies, their outcomes and recovery actions are fed back into the pipeline. This creates a self-refining model that continuously improves through feedback and new data ingestion. So the key benefits to highlight here are end-to-end automation, real-time responsiveness, model retraining with feedback loop, and this works across hybrid multi-cloud setups. Methodology summary. Our approach begins with real-time metric collection from cloud workloads. We apply feature engineering and dimension detection, followed by training using both supervised and unsupervised models. Validation includes synthetic failures via GANs. Finally, we integrate deployment with CI/CD and edge inferencing via TensorFlow Lite. I have shared a sample Python code here, which uses the PyCaret. In this, you can see how we did comparative model analysis. We evaluated several models: LightGBM, XGBoost, Isolation Forest, Autoencoder, and a hybrid AI ensemble. The hybrid model consistently outperformed others across metrics like precision, recall, FN score, and scalability with minimal overhead. Uh, Key experiment results. The SPAT framework improved MTTR by 40%, detected anomalies up to 30 minutes earlier, and reduced false positives by 25%. This allowed for more proactive scaling, better resource planning, and fewer disruptions during critical business events. Here you will see model accuracy metrics under peak load and baseline scenarios, along with visual proof of the gains in responsiveness, false positive reduction, and auto-scaling improvements. These findings prove the model's reliability at scale. Prediction, forecasting, and cost optimization results. We use forecasting model to predict CPU and memory usage, allowing the system to auto-scale ahead of spikes. This led to cost savings across compute resources, primarily due to better instance utilization and anomaly prevention. This graph displays the actual and predicted CPU and memory usage, along with identified anomalies for both CPU and memory. Industry case studies. In retail, we maintained 99.5% uptime during Black Friday and we got 35% faster response and 18% cost savings. In finance, fraud detection became 28% faster. Healthcare saw 50% fewer equipment failures. A similar success was recorded in telecom and manufacturing, all driven by proactive anomaly detection. Future research directions. Research directions. We are now exploring explainable AI with shape and line, federated learning for cross-cloud environments, multimodal detection from logs and matrices, okay, and self-healing automation using reinforcement learning. So these will soon enable fully autonomous cloud operations. Conclusion. To summarize, SPAD shifts cloud monitoring from reactive approach to predictive and anomaly detective model. It is scalable, explainable, and cost efficient. And it is proven across multiple sectors as workloads become complex. Frameworks like SPAD will, SPAD will be essential to keeping cloud system resilient and intelligent. Thank you for your time. I would love to hear your feedback or answer any questions about the framework, implementation, or future improvements. Thank you again. Have a good day.